Okay, so we're gonna draw the shear force and bending moment diagram of this beam. The first step is always to get the reaction force at support A and B. Notice that there's no force in X direction and support B is a ball. So it doesn't take any X force, and support A doesn't have X component either because there's no force in the X direction. So there's only AY and BY in this case. Gonna label them. And then we're gonna write sum of force in X to be 0. So AX is 0. Sum of force in Y is 0. We have AY plus BY is equal to the 100 Newton here in the end, plus the distributed force. And now we're going to take moment at point A to get BY. We define counterclockwise to be positive moment. So we have BY, and the distance from BY to AY is 1.8 meters. And if you use your right hand rule, BY is a positive moment. And then we have this 100 Newton force. It is negative, and the distance to A is 2.4. And then we have the distributed load. It is negative. Its magnitude is 100 times 1.2. And the distance to AY to A is half of 1.2. And then we have a positive 132 Newton meter at point A. Don't forget that. Solving this, we get BY equals 100 newtons. And then AY from the second equation is 120 newtons. And now we can do some sections here in the diagram. We're gonna do 3 sections: AA, BB, and CC. Why 3? Because we have 3 distances. We have 3 segments of distance. So there's 1 section of each segment. And then we're gonna draw the free body diagram of section AA. We have AY. It was 120 newtons. We have this given moment. It is 132. And then we have the shear force V, bending moment M. We define that if we draw the arrows of V and M on the right-hand side of the beam, downward V and counterclockwise M are positive. And then we have this distributed load. Magnitude is 100 Newton per meter. And very important thing, the distance X is defined from the origin all the way to where we make a cut. So this distance is X. Now we can write sum of force in Y to be 0. We have 120 going up minus our shear force V minus the distributed load. Isolating V, we get V is equal to negative 100x plus 120. Personally, I prefer putting the x term in front of the non-x term so that I know that when I draw the graph, I know that this is a decreasing slope. Sound of moment at point O. Point O is at where we make a cut. Equals 0. So we have the moment itself plus the given 132. And then we have a negative moment created by the support force at A. And then we have this positive moment created by the distributed load. 100 times x, this is the load, and then we're going to multiply by its distance, which is, it's somewhere here, and this distance is x divided by 2. And then we're going to isolate m. So m is equal to negative 50 x squared plus 120x minus 132. So these are the equations for section AA. Now we're going to do the same thing for section BB. The distance is from 1.2 to 1.8. Let's look at what kind of force we have. We have a given moment. We have the distributed load. We have AY, and we have this distance, which is no longer a variable, which is it's a fixed distance because our BB is here. It's more than 1.2. So let's draw it. We always draw from the right hand side, from origin. We have the distributed load. Let's say here is and then from here to here we have 1.2 meter. The total distance is x. We have downward v, counterclockwise m, and this distance is x minus 1.2. We're gonna need that. So sum of force in y is 0. We have what? We have a positive 120 minus v minus the distributed load. And that's it. By isolating v is actually 0. And then we take moment at point O, make it equal 0. We have the bending moment. We have the given 132. We have a negative moment created by support. So negative 120x. And then we also have a positive load, positive moment created by the load. So the magnitude is 100 times, I'm gonna write a dot as times 1.2. The distance, if I were to replace this, the distance here to point M, so to point O, where we take moment, the pivot point is x minus half of 1.2, which is 0.6. And that's pretty much it for the moment. By solving this, we get an expression for M, which is negative 60. And then we can do section CC, the last one, where the distance is from 1 point A to 2.4. But this time we're going to draw the free body diagram a bit differently. We're going to draw the arrows V and M on the left hand side. So here we have a downward 100 Newton along, that's it. Now, what's important to know is that right now the arrow V and bending moment M, these two vectors, we are putting them to the other side. So we're gonna flip the arrow, flip their directions. V, if you draw the V here, it was down, and bending moment is counterclockwise. Now we're gonna flip the direction. So V is upward, M is clockwise. And we're also gonna label the distance here. So this distance, it's from 0 all the way to C. And the total distance we know is 2.4. So from A to where we make a cut, section CC, this distance is 2.4 minus x. We define that x is from the origin, which is the leftmost, the start of the beam. So V minus 100 is equal to 0, so that gives me V is equal to 100. And bending moments, it's 0. We have, and this is our pivot point, point O. The point O, or the pivot point, is always at where you make a cut. So by convention, we have a negative M. And then we also have the 100 Newton force creating a moment, negative 100 times the distance is 2.4 minus x. So by isolating M, I got 100x minus 240. And now we are ready to draw the free body, draw the shear force and bending moment diagram. Let me draw very long lines. And we have 3 sections. We have 1.2 meter and then 2 times 0.6 meters. So about here, right? This is 0.6 meter, 0.6 meter, and 1.2 meters. Now we're gonna draw the shear force diagram first. So here we got x equals 1.2, x equals 1.8, and we can label this x equals 0, 1.2, 1.8, and this is x is equal to 2.4. Now look at the first diagram, the first equation we have for v, which is here. Let me just copy this. And then we can say this is v1 for the first section. We know it's a downward slope and it's a linear relationship, so it's just a downward line like that. We're gonna plug in values, and this is for 1.2 meters, right, all the way to 1.2 meters. So we're gonna plug in when x equal to 0, that gives me v is 120, and then if x is 1.2, this gives me v is 0. So I know that when x is 0, it starts at 120 and it goes all the way to v equals 0 at 1.2 meters. And then we're gonna do the second equation of v, section BB, which is v equals 0. Just put it on the side. So this whole thing is 0 here. Not gonna draw it. And then look at v3 is 100. And it's a constant, so somewhere here. Yeah, not very straight. Okay, so this is our V shear force diagram. We can label this function to be negative 100x plus 120. Okay, now we're gonna draw the bending moment diagram. Again, we're gonna draw from section AA, section BB, section CC. So we're gonna go for the first equation we have for bending moment, which is this one. See that this is power 2, so this is quadratic, and it is a negative number. It is a negative number before the quadratic, so that means its opening is downward. Positive number means this. Negative number means this. So we're gonna plug in values for it. I'm gonna say this is M1. So when x is equal to 0 and x is equal to 1.2, m is equal to negative 132. And when x is 1.2, x is, let me use my calculator. So negative 50 times 1.2 square plus 120 times 1.2 minus 132, I got negative 60. So we know that m starts at negative 132, and at this point, when x is 1.2, bending moment it's at negative 60. Negative 60 is around here, and it's a negative opening, so the opening is downward. So it's gonna look like something like that, something like that. And then we're gonna see what M2 looks like. M2, section BB, -60, it's a constant number. So it stays there. You see that when M reaches section AA, when M for section AA reaches its end, 1.2 meters, it is the same as the next M. Same thing for V. Oh, we don't have that situation here, but it's a good indication that we did this question correctly. So we know that we can draw M2 first. M2 is a constant value, -60 for this 0.6 meter. And then now we can complete its right-hand side like that. And then our M3 was this. And then we can double check. When x is equal to 1.8, M is what? It is indeed 60. It is the same as the previous M, and x is 1.4. M is what? 100 times 2.4 minus 240, that gives me 0. And this relationship tells me this is a linear line, and it goes up, which is what we have, right? We are in -60 now, and it goes to M equals 0. This is indeed an increasing slope. So the algebra is correct, logic is correct, like that. I'm gonna erase this. So this is 1.2, 1.8, 2.4. X equals 0. So this whole thing is my bending moment. And this is it for this problem. Now we can do this problem, the truss analysis, and the method we're gonna use is called the method of joints, meaning we're gonna start at I'm not gonna say a random joint, but well-educated guess joint, and we're gonna draw the free body diagram from of this joint, and we're gonna find the forces of its member, and then we're gonna flip the direction of the member, and then we're gonna develop to the next joint, the following joints, all the way until we get what we want. In this case, we want BF, BE, and CE. BF here, BE there, and BC here. So basically what we want is the free body diagram at joint B. So we have P1 and P2. They are given 15 and 6. Let me just write it here. So P1 is 15 and P2 is 6. Since at joint D, we only have 2 members with a given force, so I feel like we don't have to do the old school way, which is always to find the reaction force at the supports as step 1. In this case, I feel like I can just start figuring out the reaction at D. So let's draw the free body diagram at joint D. So joint D, I have this downward 6 kilonewton force. I also have this one and this one. Since the given force is downward, and the only one that can have a y force component force is this member, and we're gonna give it a going up direction. And since this is going up and going to the left, So the remaining one, I'm gonna guess it's actually going to the right. The direction is kind of guessing, right? You guess the direction, but you can make educated guess. And this force is F DE, and this is F CD. First, we're gonna figure out what's the angle here, which is this angle. So we have 2 meters and 1.4 meters, so we're gonna use inverse 10. Two over 1.4. And this gives me 55 degrees. Now we can do sum of force in Y. We have a negative 6 plus FDE sine theta. By solving this, I get FDE 7.32. By knowing FDE, I can write sum of force in X to solve FCD. Cosine theta. Since we get positive values for both forces, that means our assumption of their directions was correct. And FDE, it was pulling away, so this is tension. And FCD is pushing inside to the pin, so this is compression. Now, by knowing these two forces, we can move on to the next joint. Next joint, let's look at the diagram. We can go to joint C, because if you go to joint E, there's too many unknowns, and point C is a lot simpler than point E. So let's draw the free body diagram for point C. Let's do this. Forgot to label. This is for D. And when we move on to the adjacent joint, we're gonna flip the direction of this the force that we just solved. So in this case, FCD, we're gonna flip it. And coming down, we have EC. And we have this force, BC. Immediately, we can figure out that there's no force in the Y component, so FEC must be 0. Because there's no force to balance this force. So this force is actually a 0 force member. It doesn't carry any force. And very easy, we can still solve FBC. It has the same magnitude as FCD, just the opposite direction. And it is in compression. Now we have E, we have C, we also have D, so we can solve what's at E. So let's draw E. E is a bit complicated. We know that this force is 0. We can still draw it. We also solve this in step 1. this is 0. And let's go to free body diagram 1. So this is to the left, up, and then we can flip the direction like that. And we solved it. It was 7.32. And then we have a force in the horizontal direction, Fe. We're gonna call it Fe. And we also have this force. We call it Be or Eb. And we're gonna need to know angles here. We're gonna need to know this angle, this angle. So we can call this theta again, which is here. This is this side divided by this side using inverse tan. 2 over 2, that's 45 degrees. And we also gonna need this angle, gonna call it phi. Phi can be solved by using 90 minus this theta. That was 55. Now we can solve the forces. So we can solve forcing Y first. So we got FEB, this force goes up, and FED goes down. So these two forces, they must balance out using their angles. So we have FEB sine theta is equal to FED, or 7.32 cosine 35. Solving this, we get FEB to be 8.48 kilonewton. And since we got a positive value, that means our assumption is correct. It is in compression. Now we can solve f of x. We didn't include this force because we know it's 0. We can technically remove it, but I drew it here so that I can draw this angle phi. In the x direction, we have Fe. We have the force we just solved, force Eb, cosine theta, and we also have the FED force, the 7.32 sine phi. See, everything here is FEB, we just solved it. It's 8.48. You see, everything here in this equation is positive. That means my Fe must be negative. otherwise they won't balance out. Negative 10.2. And what does that mean when we get a negative value? That means our guess was incorrect. It's actually the opposite direction. So it's in tension instead of compression. And its magnitude doesn't change for sure. And now we can move on to the next joint. We solved this, we have this. So we can draw the free body diagram at B to see what's going on, and we also have this given force. This one is 15. And we have FB. Let's draw it upward. We also have EB, we just solved. Where's EB? EB is here, and its direction was in that, so we're gonna flip the direction. FEB, where is it? FEB here, 8.48. And we also have FBC, which is here, 4.2 to the right. So we're gonna flip it, 4.2 to the left. And we also have AB. The force we're looking for is this one, FBF, FFB, here, FB, we're looking for this one, which seems that we don't need the equation for X, we just need the F of Y, because everything's known, we don't care the magnitude of this force, AB, because we are not asked to solve it. So just write F of Y is equal to 0. We got positive FFB minus 15 minus 8.48. Gonna need this angle. This angle, I think we had it. So 8.48. 8.48, that was 45 degrees. By solving this, we get FB is equal to 21 kilonewton. It's a positive value, that means our guess was correct. So this is in tension. So now we have all the forces. We have this one, we have EB, the question was asking for, BF, B, and CE. CE, where is CE? Here, it was 0. So this is how you do the joint method. Now we're gonna look at the method of section, which means you make a cut. Okay, so we are gonna look at what's the force in GH here, HE, this one, and DE, this one. And that's why I make a cut here right in the middle. It's important to know that when you make a cut, the maximum number of beams or structure you can cut through is 3. Because we have 3 equations. Some are force in x, some are force in y, and moment at a specific point. We only have 3 equations, so you don't want to cut through 4 members. Like, personally, I would say make a cut here is unnecessary. And luckily, all the forces being asked, they kind of sit together. They kind of sit close to each other. So, step 1, we're gonna find the reaction force in at the supports. By observation, we see there's no force in x direction, so, well, I can still write that ax is equal to 0. Note that the support type at F is a ball. So even if there is a force in x direction, the support at F doesn't take that load at all. And then we have some forcing y. So we have ay plus fy is equal to all these 3 forces together. And then we can take moment at A to be 0. And then we have f of y times the distance here, which is 8. And then we have the 9 kilonewton force, the 4, the 7. They are negative, or just put them on the other side. So 2 times 9 plus 4 times 4 plus 6 times 7. So by solving this, Fy is 9.5 kilonewton, and Ay is 20 minus 9.5, 10.5 kilonewton. Now we are good to go. Now we can draw the free body diagram. The thing is, when you make a cut, you keep left hand side or right hand side. It's always a good idea to keep a simple side. In this case, right hand side I feel to be simpler than left hand side because we have 2 forces instead of 3 forces, right? So let's keep the right hand side of the structure. We have this triangle here. And then we have 3 forces sticking out. Let's just say this is to the left, and it is GH. We have, since it was to the left, let's do this to the right. This is guessing. Algebra will tell you if you guess right or wrong. This is D. And we have this guy, HE. And then we have a given force 7, and Fy we just calculated. I'm gonna write this. Fy is 9.5. 9.5. We're gonna need this angle, theta. Theta is equal to, theta is right here, 2 by 2, so 45 degrees. And now we can take moment at this point. What is this point? Moment at E. Because there's a lot of force passing through this point, and those forces, they don't have any effects on the moment. And immediately we can solve force GH. What's the distance? This is 2 meters by 2 meters. So we have FGH positive counterclockwise, and distance is 2. And we have the other one, 9.5, distance is also 2. So that means my GH is actually negative. We made a wrong guess. It's actually to the other side, so compression. And then we're gonna update the free body diagram before we solved the other forces. Now we can do force in X, because there's only the force we just solved and the other one HE in X direction. And immediately I can tell that we're gonna flip the arrow for FHE. So we have, well, we just updated our free body diagram, so now FGH is to the right. Minus, plus actually, because according to this diagram, our HE is also to the right. Cosine data. Solving this, we get hold on, we also have, my bad, didn't see that. Get a plus FDE. And we have 2 unknowns, so we're gonna use sum of force in Y. We have 9.5 minus 7 minus FHE sine data. Solving this, we get FHE to be 3.5. And it is in compression. We don't need to change anything. The guess was correct. And plug in this value back into f of x. We got FDE is equal to negative 12. Kilonewton, which means positive 12 kilonewton, and then we're gonna change the direction, make it in tension. And that's it.